Okay, just a disclaimer before we start this explanation. You should read this guy. Has a really good explanation. Helped me a ton with understanding the problem a little better. He also has a website. If you go to his bio and check out his website, and I think he's starting YouTube series 2. Yeah, YouTube channel on DP. You check that out there too. Yeah, read this, then I'll explain the solution, then come back here. Hey guys, welcome back to another Leetcode problem. Today we're doing problem number 1626, best team with no conflicts. You are the manager of a basketball team for the upcoming tournament. You want to choose the team with the highest overall score. The score of the team is the sum of scores of all the players in the team. However, the basketball team is not allowed to have conflicts. A conflict exists if a younger player has a strictly higher score than an older player. A conflict does not occur between players of the same age. Given two lists, scores and ages, where each score and age of I represents the score and age of the ith player, respectively, return the highest overall score of all possible basketball teams. So for example, now we have this score. We have 1, 3, 5, 10, and 15. These are our scores, and these are the ages, right? Now we need to pick a team such that the overall score is highest. And in this case, it's 34, because we can choose all the players. This is not a good example to illustrate the problem. This one is a little better. So we have all these scores, and we have these ages. We have 4, 5, 6, and 5, and we have ages 2, 1, 2, 1. The output is 16. Why? Because we can't add all the players, because if we did, we have 4, 5, 6, 5, that'd be 21, right? The reason we can't do that is because, let's say we added all of them, right? There would be a conflicting player in this case. Why? Because this one, or both ones, actually both ones with the score of 5, see, this one has a score of 5, is more than this score of 4, which the player has a higher age, which is 2. So this player has an higher age. His age is 2, and he has a score of 4, so 2 and 4. But this player has a lower age, 1, but it's more than the score of the player that has the age of 2, which is 4, right? So 5 is greater than 4. So obviously that would be conflicting, so we can't add one of them. So in this case, what they decide to do, yeah, you can just get rid of that one, and then you'll be left with this 1, 2, 1. The last 3 players. So we have 1, 2, and 1. No conflicting players. 5, 6, and 5. It's best to choose the last 2 players. Notice that you're allowed to choose people of the same age. Okay. So now we know that we have all these ages. We have all these scores, and we have this constraint where one player can't have a strictly where a younger player can't have a higher score than an older player. So how are we going to approach this problem? Very simply, we're going to first sort the array. Okay, so we're going to sort the array by their ages. So 1, 1, 2, 2. Why are we doing this? Well, it's going to make the problem a lot easier for us. Because now let's say I wanted to start mixing and matching the players. It'll take too long for me to start mixing and matching all the players and gathering all the subsets and then checking if the constraints are valid. That's something we could do, right? We could have possibly get all the possible subsets, check if constraints are met, and return the maximum of all of them, right? Of the ones where the constraints are met. That's one possible solution, but that would take too long, especially to get all the possible subsets, right? 2 to the n time. Instead, what we can do is, to make this a lot easier, we can sort the array by ages. So we have 1, 1, 2, 2. And that way, let's say I add the player, let's say I'm going through the array and I'm getting all the maximum. So now I'm getting the most possible score if I just take 1, or if I take 1 and everything before it, or if I don't. Or if I take 2, if I include 2 in my like you can say of my problem size or my sample size. So I'm just taking 1 as my sample size. I'm gonna try to find all the possible solutions for 1, then all the ones for 1 and 1, then all the ones for 2 and 2, then 2, 2 and 1 and 1. That's how you want to kind of think of it. You want to just start slowly building up your sample size until you go through the entire array. Not exactly. You'll understand what I mean. You understand how it specifically works when we go with the solution, but generally that's the idea you want to get. Instead of trying all the possible subsets, why don't we start very small and start increasing? And we increase and increase. And eventually we'll get a final answer. So we're going to first sort the array by ages 1, 1, 2, 2. And then why are we doing this? Because now if I add 2 to one of this, a subset over here, it'd be very easy. All I have to do is check if 2 has a greater score than everything before it, then I can add 2 in. Okay? So I'll sort by, I sorted by the ages, and I'll also sort it by the score. So what would it be? It'll be like 5, 5, and then 4, 6. Yeah? 4 and 6. The 2 2s have a 4 and 6. And now to explain further, let's just go through the problem and it'll make really sense. So first thing we do is we push everything into this candidates. This is, by the way, the same guy from last video. Really good solution, interviewing recipes. You're going to put everything into this array. So every candidate now has an age and a score attached to it. Then you're going to sort. You're going to sort it, like we mentioned, by the ages and then also by the score. If the ages are the same, then right, that's what this is doing. If the ages are the same, this sort by score, else just sort by the age. Once we do that, we have the DP array. Okay, why are we using dynamic programming? You're going to see in a second. What the DP array is going to store is the best possible solution after including that element in the sample size. So we're going to try 1, get the best possible solution. We're going to try 1. We're going to add this 1 to our sample size, get the best possible solution with 1. Same thing with 2. Same thing with 2. So what we're going to do is we're going to try 1. And then we're going to mix it with all the elements before it and then get a best possible solution. And then once again, we're going to add 1 to our sample size and then try 1 with all the best possible solutions before it, which in this case is just the DP at I, at the element right over here. And same thing with 2, we're going to add 2 and try with all the best possible solutions before it. Then add 2 over here and try with all the best possible solutions before it. What do I mean by that? Right now you see this. So we're going to start with, we're going to have a DP array. I have the debugger open, so it'll make it a lot easier for you. Okay. So we sort the candidates. Just doing step by step. Let's go. So we sort the candidates, and we have 1, 1, 5, 1, 1, 2, 2, right? And with their appropriate scores. We have our DP array. All zeros are first. DP of 0 will be the first one, 5, right? Because if we have a sample size of just the 1, obviously the greatest score would just be the score of that element, which is 5. So the first one will be 5. Then we start working. This is mainly just the problem. So I say DP of I is equal to candidates I1. So now DP of I is 5. We included 5 in our sample size. Now we're going to try adding it into all the best possible solutions before it. What do I mean by that? And we're going to go from 0 all the way up to I in our DP array. Okay, that's really what we're checking. Now we're going to check if that candidate before it had a lower score than my current candidate. Why? Because if let's say this was 10, or in this case it makes sense, right? This problem. So we have 2 and 4, right? And then we were checking with all the best possible solutions before it, and I'm trying to add 2 to 4 with 1 and 5, right? I'm trying to combine 2 and 4 and 1 and 5 and make it into a solution. So this 2 with this 1. But there's a conflict there, right? There's a conflict between this 2 and this 1. Why? Because this 1 has a score of 5, and this 2 has a score of 4. In this case, a younger player has a higher score than an older player, and that can't work, so we don't do that. And that's what this is checking. This makes sure, this line over here ensures the younger player has a lower score than the older player, and the older player has a higher score. Okay. So I'm going through, I'm at 2 right now, I'm checking all the players beforehand, all the players that are younger than me or the same age as me, and I'm checking. If their score is less than my score, great. I can either add it in now or I can't add it in. So I'll add it in only if what? Only if the score at that subset size, which is what DP of J is checking, the element size before it, plus my score, which is candidate I plus 1, right? My current score that I'm at, plus the total score of that previous subset, is greater than the current total score of my subset that I have right now, which is DP of I. Right? DP of I and DP of J is basically the score of that subset. Okay, so I can either add it into the previous one and check the total score, or I can just stick to my current max. So I'll do that with all of them. Right, I'll add 2 to the best subset over here, to the best subset over here, and then I'll get the maximum of that, and I'll reset my maximum. If this subset ending at 2, 4 is greater then anything we found previously, I'll set it to the maximum. Same thing with 2.6, right? Same thing with 2.6. Check over here, it's greater than everything before it. I'll set it to the maximum, and then you return the maximum. That's the solution. You can check the discussion. He has a good explanation. It helps over here too. Fairly easy, DP. Thank you, man, for this. It helped me a lot. Idea is to first sort the players by the age so that we don't have to always have to check both the scores and the age to see whether these two players can be in the same team. We sort first in the descending order of the ages. Now we know that for any player I, we can choose any player from 0 to I-1, as long as that player has a higher score than the ith player. DP of I towards the maximum score that can be obtained from ith player is included, and all the players between indices 0 and I-1. So DP of I, remember, indices 0, -1, everything behind it. This was a solution. Someone had a Java solution, took that right here. There you go. Please check this guy out. He has some website. Yeah, he has a website, and I think he's starting a YouTube channel too. Just check him out. Really helpful to me. That's that. And I'll see you guys in the next video.